So now that we finished our discussion about iterator adapters, it's time to turn our attention to the second class of adapter in STL, the so-called container adapters. As you'll see, there are three types of container adapters in STL: stacks, queues, and priority queues. The stack container adapter is ideal if you need to have some type of last in, first out, or LIFO protocol, where elements are inserted and removed from the same end of the queue, or in this case, the stack. In this particular case, a good human known use of this would be a stack of cafeteria trays where the item that's put on the top, this tray that's put on the top, will be the next item taken when a person comes by to pick up the tray. Another kind of container adapter is the queue container adapter. And this is a first in, first out, or FIFO data structure where elements are inserted into one end and then removed from the other end. And something like a queue of people waiting in line at a movie theater or at an airport or waiting to get gas at a gas station with one pump, those would be examples of first in, first out queues. And the third type of container adapter, which is really the most interesting type, is the so-called priority queue adapter. And this essentially assigns a priority to every element in the queue. And when you add a new element to the queue, you push it and it goes at the end, but then it percolates to the place it really belongs inside the queue based on its priority. And whenever you pop an item from a priority queue, you'll end up getting the item of highest priority, whatever that means in the context of whatever you're doing. And we'll talk about how you can control that shortly. So one human known use of a priority queue would be the different levels of service in an airplane. You have first class, business class, and coach class or economy class. And the idea there is that people who are in first class get served ahead of people who have business class seats, who get served ahead of people who have economy class seats. At least when you do things like check in to the airport to get your seat reservation and check in your baggage and so on. So we're going to take a look at a number of different examples of container adapters, of course, for stacks, queues, and priority queues. And you'll be able to find all those examples here at my GitHub repository. So speaking of which, let's go over and start talking about the examples. Before we look at the code, I just want to reiterate a little bit about how these container adapters are implemented under the hood. What they basically do is they provide little wrappers or decorators that encapsulate existing containers. So for example, we'll see that stack by default is encapsulating a deck. Likewise, queue by default is encapsulating a deck. And priority queue by default encapsulates a vector. And these underlying containers actually have much more functionality than is actually being exposed through the container adapter APIs. Those APIs are intentionally narrowing the scope of what the underlying container can provide and needs to provide. In particular, container adapters don't provide any support for iterations. You can't get iterators and iterate through them. They're just meant to be used by either pushing and popping and doing it in the discipline that corresponds to the protocol of the different abstract data types. So now let's go ahead and take a look at some examples. And we're going to start with the first one, which is going to be the stack. So again, remember, a stack supports the last in, first out, or LIFO protocol. And a good example would be a stack of cafeteria trays, or maybe a car with a back seat with just one door, so that the first person who gets in is the last person to get out, and likewise, the last person to get in is the first person to get out, so you don't end up crawling all over each other in the back seat. So here's a typical implementation of the class stack in STL. As you can see, by default, it takes a template parameter, which is a container, and it's going to be defaulted to deck. So it's going to have the deck being used as the default implementation of stack. I honestly don't know why they did that. I think it's a little weird. They probably should have used vector, but you'd probably have to go ask Alex Stepanoff or Dave Musser or anybody who developed the STL back in the day to find out what motivated them to do it this way. There's also a bunch of methods defined in the stack interface, and they correspond to what you'd think of in a stack. So things like, is the stack empty? Is the stack, what's the current size of the stack? Push, pop, top, all those kinds of things. Let's take a quick look at some of the methods and how they're typically implemented in a stack. Your implementation of STL may or may not look exactly like this, but chances are it'll look pretty close. So one of the parameters is just a constructor that takes in a reference, a const reference to a container, so you can actually initialize the container used to implement the stack directly without having to go through all the pushing behavior. And you can see under the hood that an instance of container is defined in the private part of the class. And that's what actually holds the contents. The empty and size methods are const. They just forward to the corresponding empty and size methods on the underlying container. Top is interesting. Top has two methods. One is going to return a non-const value type by reference, and that allows you to use it on the left-hand side of an assignment statement. And the other is a const version that returns a const value type reference, and that's used whenever you end up passing a stack around by const ref, for example, to a helper method to print it or do something with it. And so you see that there are two methods, and I'll show you how those get called later. Both of those methods are simply going to go ahead and forward to the container's back method that just returns the back by reference, but doesn't actually remove it from the underlying stack or from the underlying container. Then there's also push and pop. As you can see, push goes ahead and does a pushback to add it to the end of the underlying container, and pop will remove the item from the back of the container by using pop back. Notice also how top and pop don't do the same thing. So pop removes an item without returning it, whereas top returns an item without removing it. And that is by design. That's intended to make exception handling properties and exception handling safety guarantees more tractable and quite common in STL and C++ code to do things like that. All right, so let's go ahead and take a look at our main program. We have a little helper method called print top that will illustrate how the const version of top gets used. Here is a stack of characters, and we go ahead and we are going to push A, B, C, D onto the stack in that order. I could also have provided an initializer list to give it those values as if we were initializing it from a container, but that takes away from the fact I want to use push. So when we push the items A, B, C, D onto the stack, then of course D is actually on top, C is second, B is third, and A is the bottom of the stack because it went on first. And that's the last in, first out protocol we talked about. Then what we're going to do while the stack is not empty, we're going to go ahead and do a little funky magic here to demonstrate the non-const version of top. So as you can see here, we're going to go ahead and call top to see if top is equal to the value C. And if it is, we're going to replace it with the value Z. And you can see here how we're using top both kind of on the left-hand side of the assignment, or on the left-hand side where we're reading it. And then down here, we're using top on the right-hand side in order to be able to get its value. And then we're also using it on the left-hand side in order to be able to store the value. And when I say left-hand and right-hand side, I don't literally mean right-hand side. I just mean we're reading its value as opposed to assigning to it. Then down here, to distinguish between the const and non-const version of top, we call a method called print top. And print top, as you can see, takes a const stack ref. And therefore, the top method that's called here has got to be the const version that returns a const ref. Whereas the one that's called here, in contrast, is the non-const version that returns this by reference, but it's capable of being modified, which is exactly what we're doing when we change the top item to Z as opposed to C. And then just an interesting little tidbit, you'll notice that this version of top is also the non-const version, even though we're using it in the sort of an R value or right-hand side value-like sense. We're reading from it as opposed to assigning to it. So given that, let's go ahead and run the code. And you can see here that we are going to push A, B, C, D onto the stack, and then we go through our little loop and we pop each item off. They come out in reverse order, of course. And when we get to C, we replace that with a Z, and that's what we end up printing when we print the top of the stack. Okay, so that's the stack. Pretty straightforward. Remember, there's no iterator available on a stack, so you just have to kind of suck it up and do pushes and pops to get what you need. The next type we're going to talk about is a queue. And this, of course, is a first in, first out data structure that has you insert elements at one end, the back, and remove elements from the other end, the front. And again, think about something like a queue of people waiting in line to go see a movie or to get gas or whatever. This particular implementation also is going to use deck by default, but you could change it. You most likely wouldn't want to change it to vector because vector doesn't support efficient removing things from the front, but you could change it to list, and that would work just fine. So here's kind of a canonical implementation, much like we looked at before for stack. You can see here how we have a template that's parameterized by a container, and we then have a queue constructor that could be given a container. So if you want to pre-initialize the queue, you can do that, and that'll of course come down here and assign to the container that's defined as the data member coming from the parameterized type here. And then we've got empty and size, which just forward again to the empty and size in the container. And now we've got some other methods: front, push, and pop. So a couple things. First, front behaves very much like top did. So if you recall top, there were two versions of top, one that was non-const, one that was const. Same thing is true for front, and all front does for both versions is just go ahead and forward to the front method on the container, which would be for a deck or a list. If you try to instantiate this with vector, it's going to fail because there is no front method defined on a vector. Push and pop do interesting things as well. So you can see that when you push an element onto a queue, it adds it at the end with pushback. But when you pop an item from the queue, it pops it from the front. So we push to the back, pop to the front. And that's what makes this a first in, first out data structure and protocol, as opposed to a last in, first out, which is what we used with stack. Now, something weird went on here. I don't know why they did this. Using push and pop to mean NQ and DQ just seems a little bit odd. I would prefer to use names like maybe, I don't know, put and take or get and put or NQ and DQ or something. But they chose push and pop for whatever strange reason. So you just have to kind of suck it up and get used to that nomenclature for the terms. So let's come down here and take a look at the actual implementation or the usage of the queue. Once again, I'm going to have a little helper method that prints off the front item using a const ref. Down here, we have a queue of strings, and we're going to push 1, 2, 3, 4. And here you can see that we're adding them into the queue, and they would go in that order. So 1 will be at the front, followed by 2, followed by 3. And this time, when we walk through the queue, while it's not empty, we're going to go ahead and pop, which again seems weird on a queue, but whatever. And in this case, if the front item of the queue equals 2, we're going to replace it with boo, just to rhyme. And then we're going to go ahead and print the front item. And you can see that printing the front item is going to have a const queue ref. And so therefore, this call to front will be the version that's the const ref version of front, whereas the versions that are used here are going to be the non-const version. So again, this version is reading the contents of front, and then this version is getting back a reference so we can use it on the left-hand side of an assignment statement. So we're using the return value of front here as an L value, whereas up here we're using this as an R value just to read it. When we're all done, we pop the item, and as with stack, pop is firmly decoupled from front. So if you want to read the item, you use front. If you want to remove the item, you use pop, but you can't both remove and read the item at the same time. You have to pick which one you want to do at any given point. And that, again, is somewhat different from the way Java works, where they combine pop to remove the item and also return it. And that's because Java has reference semantics and a different way of passing things around than C++, which is doing things more with values and so on. Okay, so that is queue. I think you'll agree with me that stack and queue are pretty simple and probably conform to your expectation of what a stack and a queue are, more or less. The next type of container adapter, however, is different and maybe more interesting in a lot of ways. This is the priority queue. And this has a similar interface as stack does and queue, but the difference is when you push something into a priority queue, it's going to go ahead and insert it in priority order relative to the other elements in the queue. And when you remove something from a priority queue, it's always going to remove the item of highest priority. Now, you get to define what high and low priority means using C++ operations like operator less than. But the key point is it's not based on how long the item's been in the queue, it's what its priority is. And of course, there's lots of examples of priority queues in real life. We talked about queuing up at an airport, waiting to get checked into a flight based on how much money you paid, or whether you have frequent flyer miles or whatever got you to the front of the line. You can think of lots of other examples where people do things in priority order. So the other thing to note is that the priority queue container adapters actually defined in the queue header file, along with queue. So queue and priority queue both occur in the queue header file. And under the hood, by default, it uses the less functor to organize things. So by default, priority is based on less. And we'll see how that manifests itself here in just a second. You can change this. I will show you how to change this. And it also is implemented under the hood by default by a vector that's been heapified. And heapification is basically a process of taking a range of elements, like say in an array or a vector, and then converting it into a heap, which is a data structure that's known as being partially ordered, almost complete binary tree. So what that means is, if you think about a binary tree, what you have is you've got the item at the top of the tree, which will be the item of highest priority, and then its left child and its right child are guaranteed to have values that are less than it. But it does not provide a total ordering. It just provides a partial ordering. And it turns out that converting just an arbitrary array into a heap takes linear time. And then once you've converted something into a heap, you can search through a heap to find the item of highest priority and then reconstruct the heap property again in log n time. So of course, things like heap sort work very well by building a heap and then going ahead and removing each item and putting it in the right place into the array as you continue to heapify what's left over. We're not going to show the actual implementation of the heap, but be aware that that's provided in STL as some of the helper algorithms that you can use, and we'll talk about them later in the course. So here's a typical implementation of a priority queue in STL. You can see here that priority queue is parameterized by type name T, by the container, and it defaults to vector of type T, and also by a compare functor, which defaults to less for the value type of the container. And so this is how you have to write the code, or how the STL implementation has to write the code to get all those types to match up properly with generic programming. The actual implementation of the priority queue has a constructor where you can pass in the compare operation and also the container. So if you want to go ahead and stash those things away, you can. Otherwise, you can just use the ones that are defined by default. And then there's a couple of methods like empty and size that work exactly the way they work with queue and stack. They just forward to the corresponding empty and size methods on the underlying container. Then we have a top method, which will return the front item in the underlying container. And keep in mind, this has been heapified, so that means that the front item, which is the root of the tree, will always be the item of highest priority. So it always takes constant time to return the item of highest priority. Now, the other two interesting methods here, which are a little more complicated than the adapter methods for stack and queue for doing push and pop, are push and pop. And what push does is push adds the item to the end of the container, and then it goes and it calls the push heap method. And what this does is this takes the object that's been added at the end of the heap, and it reheapifies the underlying container. Let's assume it's a vector for sake of argument. And what that means is it basically bubbles that value to the appropriate place in the vector by swapping items until it goes to where it belongs. So that basically takes a very short amount of time, takes log n time to reheapify an element once you've put it into something that's already a heap. Then pop goes ahead and pops the heap, which will rearrange the underlying data structure to get rid of the item of highest priority, and then that item will be removed from the end of the container. It'll basically put it back at the end, and it'll be zapped off the end of the container. So that pops the top item off, the item of highest priority, and then reheapifies things by using pop heap to restore the appropriate relationship to make this a partially ordered, almost complete binary tree. All right, so that's a quick summary of how things work under the hood. It's a really cool implementation if you ever want to spend time poking around through it. Let's take a look at how we can actually use this particular priority queue in our example. So what we're going to do is we're going to define a struct called place, and it's going to keep track of a destination and a distance from some origin. And to make the example fun, I'm using examples from my neck of the woods in Tennessee, where I live about 21 miles from Nashville, and 15 miles from a place called Green Hills, and about 3 miles from a place called Cool Springs. So you'll see how that gets used in a second. The place struct is going to keep track of the distance as an unsigned int and the destination as a simple string, which I often use in my examples to be able to kind of show what's going on under the hood. I define an operation to be able to print a place. We'll see how that works in a second. We make that a friend. And then I have a constructor that creates a place from a simple string, destination, and an unsigned int distance. So it just goes ahead and sticks those into the appropriate data members. And notice how it uses the STL move operation to do move semantics, which speeds things up a bit and doesn't end up making extra copies. A very important method here is operator less than. We have to define operator less than if we want this to work properly with our underlying priority queue. And that's because it uses operator less than on the classes that it's instantiated with, or the struct that it's instantiated with, in order to determine the ordering in the priority queue and in order to determine what's the object of highest priority, the item of highest priority. In this case, operator less than is going to check to see whether the distance is less than the distance that's passed in as a parameter, and that'll return either true or false, depending on what you do, or what the properties are of those parameters. I also, for various reasons that you will see in a moment, define the greater than operator as well. And that works nicely if you want to change less to greater when we instantiate our priority queue. And you'll see how that works in a second too. Here's the IOStream insertion operator that prints the contents of a place. So you can see it goes out and prints the destination followed by the distance with a space in between. All right, now that I've kind of set the stage here, we can now finally talk about an example. So this is going to use the priority queue to print out city names and their distance from the city I live in, which is Franklin, Tennessee. And the output is going to be Nashville 21, Green Hills 15, and Cool Springs 3. So that's the sorted in the item that has the highest priority, which in this case is the larger number by default. How we get this to work is we make an instance of a priority queue instantiated with a place. By default, that uses the less functor, so it orders it that way. And then I go ahead and I'm going to add a bunch of things into my priority queue. So I'm going to in place Nashville with 21 miles. I'm going to push a place of Cool Springs, which is 3 miles away. And then I'm going to push in, let's say, Green Hills. I didn't change this from a previous rendition. So I say Green Hills, and that's going to go ahead and push that into the queue and put it in the right location. And that'll be 15 miles away from where I live. And notice how this defines an instantiation of place, and then we actually push that instantiation. And the reason I did this was to show you the different operations for adding things into the priority queue. So let's go ahead and take a quick look and see what methods these actually call. The InPlace method, as you can see here, uses the variant of this that takes variadic template parameters and uses the magic forward mechanism. So this is going to be very efficient. It's going to do basically construction in place. And after we put it into the right place, then we rearrange the heap properties to make it prioritize properly. We're then going to go ahead and push with an anonymous version of a place, and that's going to use this version, which is the R-value reference version, which uses the move semantics here. You can see this uses pushback with move, and then it reconstitutes the heap property. And then the final version, we're going to pass in an object of type place, and that's going to use the const ref version of this, and that's going to use just the pushback. It doesn't use the move semantics in particular. So those are 3 different ways of being able to put things into a priority queue. Given a choice, I would recommend aiming for InPlace if you have user-defined or STL-defined classes that you're putting in there or objects you're putting in there, because that'll do a better job of optimizing, as we'll see in a minute. Then, while the queue is not empty, we're going to pop the item of highest priority and print it, and then we're going to remove the item. Actually, I should have said we're not going to pop. We're going to take a look at the item of the highest priority by top, and once we've printed it, then we go ahead and remove it. So let's run this program, and we'll see what we get as the results. So there's a lot of output here, and that was deliberate. I wanted to be able to show you the difference in complexity of doing in place, which is really simple, just basically creates it in place, versus this version of push, which has a few extra operations in the hood using the move constructor semantics. So it's still fairly lightweight, not doing a lot of extra copies, doing no extra copies actually, but there's a few extra calls to these other constructors. And then finally, we do this version down here, which, as you can see, actually ends up calling the copy constructor. So that's actually going to have to do a copy. So there's extra overhead there for that one. There's also, of course, other things going on, because every time we put an item into the priority queue, then we have to reconstitute the heap, and that may move things around. But the key point is that in place has the lightest weight semantics. So try to use in place. And oftentimes, if you don't use in place, then the IDE will come and tell you, hey, use in place as opposed to push or pushback or whatnot. You can see that when we go through this little loop at the end, it prints out Nashville being the item of highest priority because it's got the highest value. Green Hills comes second, followed by Cool Springs, which is the closest. Now, just for kicks, I can trivially come along here and I can change this from being the default behavior to being a version that uses greater. So by default, it uses less. Now we're going to give it greater. And when we run this code, we're going to see that what we get as the output is that now Cool Springs shows up as the item of highest priority, followed by Green Hills, followed by Nashville. So it's reversed the order. And that's because it used greater rather than less. And you'll also notice that I snuck in a deck here instead of using the default, which is going to be vector. But let me go ahead and set this back to the original value so that next time I run this program, it'll start out with the default values for the container type and also for the functor that's used to order things. So that's the end of our discussion about container adapters. As you can see, stacks and queues and priority queues are all useful data structures, but be aware that they have been restricted because there's no iterators, and there's also lots of other things you really can't do on them that you might want. But I think it's worth knowing about these, and anytime you feel the urge to use a stack, I recommend you take a look at the container adapter version of stack or queue or priority queue first before you go ahead and implement your own version.